Our speaker this morning is Magdalena Czubak from the University of Colorado at Boulder. And she will be speaking on the formulation of the Navier-Stokes equations on Riemannian manifolds. Thank you, Magdalena.
Thank you. Thank you for the introduction, and I'd like to thank the organizers and Professor Ebin for the invitation. And it's a great honor to have a chance to speak here today. And also it's a great pleasure to have an opportunity to talk about this work in front of Professor Ebin, because every time I talk about Navier-Stokes on manifolds, even if I would like to emphasize a different aspect than what the topic of today's talk is, this topic always comes up. So I always talk about, I mentioned Professor Ebin's name, and I always talk about his work. So it is a great opportunity to be able to do that in front of you. So thank you. And congratulations on your retirement. And I hope it's the same retirement that I would like to have starting right now, that you retire and you're doing math. So, okay, let's begin. So the topic is the formulation of Navier-Stokes on the Riemannian manifolds. And the question, in a way, is very simple. What should the equation be? And I thought to motivate it, there are different ways to motivate the problem. And I think given the content of this conference so far, I would start with the Euler equation. Because usually I start with the Navier-Stokes in the Euclidean setting, and then I move on to manifolds. But in this audience, I think at this point, it's okay to start right away on manifold. So Euler, if you're looking at the, let me write it this way, non-stationary equation, then we have partial t of u, and I'm writing it in the Eulerian coordinates plus gradient equals 0. And depending what problem you're interested in, you will have initial conditions and possibly boundary conditions. So in this talk, we would like to emphasize Riemannian manifolds. So even here, one could start with this question: why do you want to talk about this equation of manifolds? Again, in this audience, I think at this point it's clear why. For me, mathematically is just really beautiful, and there are really nice questions that ideally, at the same time, I guess my preference is if things can be physical, if the problem that you're studying models some physical phenomena, but the mathematics that shows up, if you're willing to look at things in more general setting, is just too nice to ignore as a mathematician. Okay, but I'll come back to this about the physics. So we're looking at a Riemannian manifold, and if this is Euler and Eulerian coordinates, and again, this has been said many times, but maybe I'll repeat it. Warning. U is the velocity vector field. So uxt means the velocity of the fluid at position x and time t, and p is the pressure. So if I would like to now study the Navier-Stokes equation, then the easiest way to introduce what the equation would be is to add the Laplacian. And if I write it here, I would be adding the negative of the Laplacian u. So the question is, if you're on a general manifold, what is the Laplacian of u in this context? So I think this is the easiest way to see the possibility, and maybe it's not obvious what it should be, what the equation should be. If you're working with functions and you're on a manifold, then there's a clear choice. Okay, so for functions, we have an operator that's usually called Laplace Beltrami, Laplacian, and in coordinates, different ways to write it. I mean, if you're thinking that the Laplacian is a divergence of the gradient, then if I like to have a minus sign, then we'll have the grad say of function, I call it f, then it would be negative 1 over square root of g in some choice of coordinates. We would have something like this. metric Gij dxj f. This is a very nice operator. But something goes wrong if I would like to use it in this setting. And maybe it's obvious, but it's not always obvious. I've been told it's obvious that you can just use this. It's not, in fact, you can't. You cannot use this because you're interested in a vector field, right? So you would like to have an operator that acts on vector fields, and as nice as this acts on functions. So you need another operator. Okay, so now you move on to the context of vector fields, and you ask, are there Laplacian type operators for vector fields? And the good news is that yes, there is an operator, but the problem is, maybe bad news, there's more than one. Okay. So for vector fields, the first one that in a way, if you like thinking divergence of a gradient, the first operator, the most natural to look at is the so-called Buckner Laplacian, which also has many names. Sometimes called rough Laplacian, place Laplacian, even Laplace Beltrami I've seen, and it makes sense because if you start writing minus divergence and you use the same symbol for U, it looks exactly the same. But the big difference is that U is now a vector field. So this is not a gradient, this is the covariant derivative. Okay, so it's a different operator. I could write it in coordinates, but I don't know how. So in the choice of a frame, you would have something like this. In some choice of coordinates. Then you need to expand what this is in the coordinates. Okay, so this is one operator. Another operator that you could use is an operator that's very nice if you like thinking about forms, and also coming from vector fields. You might have seen something, I'm sure you have, that it's written in terms of curl. There's an operator written for vector fields that uses the curl. And the analogy of that, if you're working with differential forms, would be the Hodge-Laplacian. So saying an analogy, because for geometers, this is obvious, and sometimes we identify these things without saying anything, that if you have a vector field and you're on a Riemannian manifold, then there is a natural isomorphism between the vector field and the corresponding. There's a unique one form that corresponds to it, and you use that metric to obtain it, and it's called musical isomorphism. So using that, you can start with the Laplacian that's defined using curl. Then you find the right way to think about curl in terms of D, and you obtain the following. I'm using the negative. So actually, because I'm using the negative, I don't write it now, because D star has a negative built in it. D star of U, and as an analyst, I'm precise. It's the U is a vector field. Then I put U flat to make it the one. Okay, so D is the exterior derivative, and D star is its formal adjoint, or you can do divergence. So for students, if you're one form, D of U is going to give you one extra degree. So from a one form, then DU is going to be a two form. If you're a one form, D star is going to give you a function, which makes sense to think of D star as divergent, right? Star acts as a divergence. I apply the star to one form, I get a function. Right, so for divergence-free vector fields, D star of U would be 0. So this is another operator, and even though they look different, they're related. You can show they're related. It's a computation using Ricci identity. You can show that the Buckner Laplacian, and minus the call it BW identity of the Weizenbach formula, gives you that negative divergence of where the derivative of U is equal to the Hodge-Laplacian. This E plus the star of, let's work with forms, simpler. You flat, and I need one more term. The extra term that we have is negative Ricci of U flat. So, again, for geometers, it's coming out, but I don't think it's completely obvious right away if you haven't worked with this. So Ricci is a two tensor, so it acts usually two vector fields, right? So prior this is not obvious for by P, but you can think you raise the index or write it for the abuse of notation. Well, so here's the operator I want to define, and I'm defining it saying I have regular Ricci that we know, and I plug in U. So here's U flat. Ricci acts on vector fields, so now it's by U. And then I need this blank. So it acts now on vector fields, so it becomes a one form. And depending what I'm doing, I'm writing the equation, I either stop or I do shut to make it a vector field. Here we're writing it for forms, so I can just stop writing. Okay, and again, I'm using notation, this Ricci. Okay, so even though they're different and related by this Buckner-Weizenbach formula, and not done writing the operators here. There's another operator, and this is the one that was mentioned by Professor Ebin in the paper that we heard a lot about at this conference. And from my perspective, I've been looking at the remarks regarding which Laplacian should you use. So at the end of their, you're looking at the paper, at the end there's this remark that says that actually the correct, they put it in quotes, operator that you should have when you look at Navier-Stokes is neither of these. Okay, and what should it be? Let's call it L. That L of U is a 2, or technically the U sees 2y. There's sometimes people write that star, which is the formulation of this operator, okay, but it's equivalent to looking at the divergence, and maybe again I'll try the minus consistency of that U. What is that U? If or say U flat, if we have one forms that U flat in coordinates, you can write it as 1/2 for a derivative here. So I take components I U J plus J UI. So you're looking at a symmetric plot of it, right? So this is the deformation tensor, and if you're working with fluids, you most likely have seen this, because on the Euclidean space especially, this would be just regular. Okay. So how is this operator related to these two? It's related using again Ricci identities. You can show that L of U is equal to the Buckner Laplacian minus another Ricci, after Ricci comes out. There's actually term involving divergence, D star, but if I'm assuming I'm working with divergence vector fields, that would be 0, so I'll just ignore it. Minus Ricci. And because of what I wrote here, I'll divide it so we have everything in one line and write the question here as well. Star. Flat. So then I need another copy of Ricci. So there's this nice relationship between all of these three Laplacians, and what happens on our end? If you're looking at the Euclidean space, they're actually all the same. Because what happens on the Euclidean space, the Ricci term is 0. So they're all equal to one another. But if you're on a Riemannian manifold, then they're not the same, right? They have this nice relationship, but between this, they're not the same. So which one should you be working? You're reading the paper and you're reading the remark, and you say, yes, I want to work with the operator that Ebin and Marsden said. They said it was the correct one, right? But then you look at the paper. And this is the interesting part that I hopefully I'll hear more about today, that if you look at the paper, in the paper, they're not using that operator that they said at the end. They're using the Hodgkin-Bach. And the remark is made in what's written as note added improved. So this led to some confusion in literature because some people have been writing papers saying, oh, Ebin and Marsden use the Hodgkin-Bachian. They're using the Hodgkin-Bachian. But then other people are saying, well, there's that remark, and I've been one of those people, so I would like to follow them because they said that's correct. And they give a reference to a book by Seren. And another important remark is that they say, if you're working on an Einstein manifold, that this is the one you would like to work with. And comment why was special for Einstein manifolds. For the Einstein manifold, Ricci is a constant times the metric. So this term is very easy. You essentially have a linear term with constant dependent. Okay, so it's not clear, and what should you do? So again, you could just write papers, making a choice, and that's what we've been doing for a while, but people keep asking you about this. So you start thinking, can we try to come up with more arguments? And this is what we started doing back in 2016 with Marcelo and Chi-Hin Chen. We wanted to write a paper that provided some more evidence for why we want to use the Ebin Marsden. So I would like to tell you more about this. And it's also related to the argument that Ebin and Marsden made with that. So, you can say, oh, somebody told me to use this, I will use this operator, but you can also say there is a physics, and that's what Ebin, I believe, and Marsden meant, that it's correct because, so here I have, okay, so I should change this with NS, so we added the Laplacian. So here it's written as I would say, oh, as a mathematician, I would write it this way, because I like to think I have a linear equation. I'm thinking maybe if you want to think about it as a heat plus a nonlinearity plus gradient, that makes it part of why it's a system. But if you have a physicist or an engineer, maybe you would like to write it differently, right? So another way to write this, you could write it in this way. Fraction U minus graph P. So why this might be more physically natural is because the equation can be derived from Newton's second law, F equals ma. Right now it's switched. So ma goes with this word and F goes here. So this expression can come from forces. So if and this is the motivation from continuum mechanics, which that's when Ebin and Marsden refer to Seren's handbook. And again, if you're someone who works in continuum mechanics, this is obvious what I'm going to say, that yes, of course you should do this. So why is this obvious? So continuum mechanics, you're thinking you can show, you can talk about two types of forces. You can talk about volume forces and surface forces. So volume forces could be, for example, like gravity. They're often denoted as a function F, as a forcing function. So right now we don't have it. So the forces that we do have are related to surface forces. And you could write it as a divergence of T. So T is the so-called stress tensor. And it's a physical argument that you make, what pieces should it have? Okay. And one piece would be exactly coming from the normal stresses from the pressure. And this is the only piece you would have with your stationary fluid or viscid. But if the fluid is in motion and there's viscosity, you would have a term that you go through a derivation, you make some arguments why this is the case, that for divergence free, so there will be in general other terms, but I will ignore them, you would have 2 times that yeah, 2 times that u, and then if you keep in track of viscosity, you would have a viscosity coefficient here. So this is a physical argument. I'm lying. No one's complaining. I'll be taking divergence. So I want P delta I like this. Okay, when you take divergence, you would get gradient. So again, if you believe in continuum mechanics, you would have no objections that this is the right operator. And again, this is the operator that we would get if we would get the Ebin and Marsden Laplacian. Which, by the way, I've seen papers now that they call this Laplacian, Ebin and Marsden Laplacian. Okay, so this is one argument coming from continuum mechanics. And we talked about this a little bit in our paper with Marcella. In that paper, we also had 2, well, actually, so this was just an introduction, and then we had 3 viewpoints. So the first one was, and I'll just say it in words maybe, was an argument. At first, I was feeling like, oh, it's an argument for the Ebin and Marsden Laplacian, but actually was an argument against Hodge Laplacian. We showed that if you would like to formulate a Navier-Stokes equation using the Hodge Laplacian and go through the Leray-Hopf formulation, so you like to have weak solutions in appropriate function spaces on the manifold on H2, so hyperbolic plane in 2 dimensions, you wouldn't be able to get energy inequality. We're able to do this for both the Stokes equation and the Navier-Stokes equation. So no energy inequality. So if you don't have it, how are you going to develop the consistent theory? So to us, that was an argument against the Hodge Laplacian. But at the time I took it, oh, it means then it has to be this one, right? But to be precise, it really is an argument against the Hodge Laplacian. Another thing that we've looked at, which the referee didn't like to the details too much, but the argument I think is still a good argument. We looked at something that Marcelo can tell you more about. We looked at the non-relativistic limit. So this is when you assume that the magnitude of the velocity vector field is much less than the speed of light, and you ignore all the terms that would show up. Then there are some issues which there were new developments since that there's no one consistent theory that everyone agrees on in the relativistic fluid. So we took the ones that have been most widely used in the literature, and on all those, when we took the limit, we were able to derive the Laplacian coming from the deformation tensor. So that was another signal that perhaps this is the right one. And what I really would like to talk about now for the rest of this talk is the third argument. So you see, I would talk about some results related to fluids, manifolds, and again, often this would come up. What is the right equation? And actually, initially, we tried to work on all the different ones to see, can you do whatever we would like to do for if you're using different Laplacian, just out of curiosity. So this topic of what's the right one would come up, and different people had different thoughts. And one of the suggestions was by Steve Preston here, and also Doug Wright at Drexel, who said, look at restriction arguments. Maybe I'll write this here. Restriction arguments. So this is how we've been referring to them. So what does it mean? It's very intuitive, nice idea, that everyone agrees, and they are the same. The Laplacians are all the same in 3D. Okay, so take a vector field in 3D, apply a Laplacian to it, regular Laplacian.
You mean R3?
Yes, R3. I said R3. Sorry?
You said 3D.
Well, 3D or R3. Okay, I mean, okay, when I say 3D, I mean Euclidean. But yes, thank you. Yes, R3. R3 in the Euclidean setting, it's flat, very boring. Well, you're doing. But from the point of view of geometry, it's boring. Anyway, the Laplacians are the same in R3. So you can start with a vector field in 3D, flat space, okay? Apply the Laplacian, and now restrict it to a sphere. And see what you get. So we tried doing this, and even right away there were some other issues, which now I actually understand what went wrong. But okay, if you start with a vector field, let's do this. We looked at S. Okay, so we were thinking S2 is embedded in R3. So you can work with spherical coordinates. And this vector, and assume that if U on S2 is equal to 0. So you can start with this thinking that if I have a point P in S2, this is a vector field on the sphere. Okay? But you can also think that it's not just the vector field on the sphere, that I can think of this as a vector field on R3. And if instead of flagging in P in S2, I will just evaluate these vector fields at any point in R3. And the important thing here is that U, right, that U P is just a function of P and theta. So if you go away from the sphere, it doesn't change. And so to us back then, this was the most natural way to think about a vector field. If I wanted to restrict or extend between S2 and R3. Okay, so we took this vector field. Then we looked at the corresponding one form and we computed, if you're looking at one forms, then the Hutch Laplacian is very nice. But again, we did it using the Hutch Laplacian on R3. So we applied D star D to U flat. And again, since I'm assuming it's divergence rate, which actually I should add something. Yes, so before, but if you remember, the Hutch Laplacian has DD star in it as well, right? Here I'm saying that U is equal to 0 on S2. If I look at this vector field, the way it's written, and you compute what divergence is on R3, you can show that as written, this is also a divergence free on R3. So it's very natural, right? So then the other piece from the Hutch Laplacian, it's a computation. There's extra piece. Because I don't have the U row, if you're thinking about why. So D star of this is equal to 0, so I can just look at that. Okay. And then as a geometry, I probably should write the pullback by the inclusion map, but let's be analysts, I'll say I'll just restrict it or evaluate it on the sphere. What do you get? So it's a computation, then you see that you get the following. That you have pieces that would come out from the Hutch Laplacian on the sphere, so this is looking interesting. And then we got negative 2 U flat. I'm on the sphere in 2D, right? So on the sphere, the curvature is 1, okay? So this is exactly negative 2 Ricci, and on the sphere, Ricci is exactly in 2D, it's exactly U. And this term is exactly negative 2 Ricci U. Okay, so we saw this and we thought we're done. This is another argument. This is so nice. How can it be anything else? Right? Do you agree? So nice. So yes. But see, so time goes by, and then we started talking to Tsuyoshi Nida, who's been something Anton knows about this, interested in an ellipsoid. So an ellipsoid is so a sphere is a nice thing, right? Ellipsoid, no more, but it still has some nice symmetry. So what would happen with this argument on an ellipsoid? So we started looking at that. And as interesting as it was very painful. It was also pandemic to start. So you have in some ways, more time, less time. So you do a lot of computation, right? You start computing, it's the same idea, right? So consider an ellipsoid. So we chose it to make it look like this. So the direction, we were assuming it works for any A, but writing that assuming that the direction is A bigger than 1, and here is 1. This is something that looks like this, and you can put on a coordinate system on this that in ways mimics the spherical coordinates, and you start computing, and you start with the same thing. Now this B would be it's 0. The first issue that we have, and it took us some time to understand there was actually only a technical issue, was that this nice correspondence that if U is divergence free here, then if I just start thinking about it like that can feel like this, then it's going to be natural divergence free on R3 doesn't work anymore on the ellipse. So we have to find a way to think about it. Now I think we understand that as nice as this was, this is only a special case. If you start thinking about general vector fields and restricting them and trying to match up the divergence, what you really are doing is solving an ODE if you set it up properly, an ODE in the radial direction. So you can do it's exactly the same for the ellipsoid. So even though the divergence first looks maybe this is not natural, it's actually, I would say, as natural as the sphere. Somehow sphere maybe is psychologically it's easier to think about, but the procedure you can go is exactly the same with this in the second. We updated the paper to actually talk about this more. So you can deal with the divergence recognition. The bigger issue, I think, is that you start computing this here, you will get the Laplacian. Okay, so this is very nice. No, there. But the rest, it's not good. I'm supposed to say this because the first thing, it's a mess. Okay, it's a mess. This was a very nice, beautiful computation you can do one up. Okay, right now. But this, no. A lot of extra terms, and I've been writing them, but I'm thinking about trying not to write it. See if anyone likes the full formula. I'm happy to write it, but maybe I'll write one more term just to illustrate. So we got a term that looked like this, was the double. See, it's not even simple to write this one. Minus plus I will call it LOT for lower order terms. Okay, what is this L and what is this? So first, L is the lead derivative of the one form. Okay, and rho is the defining function that we're thinking as playing the role of the radial function for the sphere. So it's a defining function for the ellipsoid. And you're taking its gradient and taking the derivative of the form. And it's a double derivative. And this stuff there, you look for Ricci because it had a Ricci here. You would like to find it here. No Ricci term there. If I lower order term, then the derivatives, all the derivatives, with some constants. And what's interesting is that in the case of the sphere, the Ricci is hiding in this term. So, okay, so what does this mean? You need something because first you can say, okay, the formula is best. right? So you can complain about that, but I think more interesting is that you start looking at this, the fact that I have a double OE derivative here, you end up taking two derivatives. So once you start taking the derivatives, two derivatives, which direction? Well, both is the defining function, it goes away from your surface. So you're taking the derivatives of your vector field away from the surface. So that means that what you're going to get actually depends on this vector field one, on your extension or the vector field that you're working with. So when we saw this, so with my postdoc colleague today, one weekend with her class, we started computing what would happen if we worked with this formula, because the nice thing with the coordinates that we set up was it reduces to what you would have for the sphere. Okay, so we said let's play around with different extensions and see what we get for the sphere. And the fascinating thing was that you can choose different extensions. So sure, we can get the formation Laplacian here, but you can also set it up that you can get the Hodge Laplacian, you can get Buckner Laplacian, essentially you can get whatever you want. That it all depends on the extension, even for the sphere. Okay, so this, in a way, we got lucky. We wanted something and we got it. So we didn't really question it anymore. And somehow, you see, this was very natural to write it in this way. But you see, what's special about this vector field? So it's written spherical coordinates. And in a way, I've been saying, when we look at the extension of it, we're doing nothing, right? By doing nothing, I mean, I'm not changing, not modifying these functions, right? What if you don't like spherical coordinates? What if you like to work in an orthonormal frame? If you like to work in an orthonormal frame, instead of writing these vector fields, you would normalize them, okay? And then you would have some component functions. And then you can think, now I'm going to work with a vector field that I do nothing to my component functions. You can think that this is the extension by parallel transfer in the normal direction. Norm stays constant, and you didn't modify your vector field. If you work with that one, that's the one that gives you the Hodge Laplacian. And another thing that came up in all this was that someone already thought of this. No, it's not surprising because it's very natural to start thinking about these restrictions. We found a paper of Orszag from 1974 where he has, I think the focus of the paper is numerics, but he has this footnote. He's interested in the sphere. He has this footnote that depending which, how you think if you should be scaling or keeping the norm the same, what Laplacians you can get. That you can get Hodge or the one with the Ricci term. Okay, so this was already pointed out in 74. So you can use this work with Tsuyoshi as a generalization to the sphere. And another, what I think is nice is that this explicitly shows you, so Orszag's paper has explicit vector field complexity. Here, we're writing a general formula that will work for any extension. Okay. So how much time do I have? Okay, good. So we do this for ellipsoid, but you see, look at this. Now it doesn't look so bad because I'm ignoring these terms, right? But the computation was really painful, right? And you're thinking, okay, maybe there's a better way to think about this. So here we have the Hodge Laplacian, but what if you worked with Buckner Laplacian? All the Laplacians are the same on R3, right? So I can work with any Laplacian that I want. If you work with a Buckner Laplacian, you can get a different formula. And to motivate that formula, I will do some geometry or more real geometry. I don't know how you want to call it, but I will talk about Riemannian submanifolds a little. And try to also connect it to why these restriction arguments are nice. Yes, please.
So when you go D star D U flat, should that not be restricting to the ellipse on the?
Yes, sorry.
Yeah,
I didn't have.
Yeah.
Thank you. Yes.
If you can permit, if this question is to be voted, then don't answer, but
Go ahead.
in what sense is the Laplacian that we put on the right-hand side of Navier-Stokes in R3 the right one? I mean, so.
You mean even in the Euclidean case?
Yeah, I mean, just to ask that question.
I would say
is there-
continuum mechanics right now. My first answer would be continuum mechanics, right?
just
Because
the
look,
premise-
I mean, you have the deformation, right? But it reduces to the Laplacian. Okay, maybe we can come back at the end.
Yeah.
No, I think, right? I think it's yes.
Just because this premise is that you restrict a Laplacian that we assume is the right one on Euclidean, and that's how when you're picking on. the
Sure.
manifold. So, but if.
Well, if you
You're
believe in
asked-
continuum mechanics,
Yeah.
right, it's clear. Okay, let's come back maybe at the end. Yes, it's a good question. Yes.
Okay.
Right? No, you see, I really would like to get any comments, you have any thoughts, as long as you're not too angry, please tell me, okay? Because some people get angry about this, right? It's controversial. And but I think it's very interesting, right? To look at all these different perspectives and to try to understand things. So again, we're trying to understand from the restriction, and you see, let me be a geometer now, okay? And talk about how do you define directional derivatives on a submanifold, okay? And more specifically, let's think, say you have some, well, we can still call it E, and we can do first rate. Okay, so you have this, well, let's change it to M. So you have a Riemannian submanifold embedded in R3, or you could do Rn. And if I take a vector field, so xy in a, so if I choose point P, I have vector field xy in the tangent plane TPM. I can talk about R3 comes with a natural Euclidean connection that, so let's write R3 with, this is the Euclidean connection. We can consider what is the covariant derivative, or yes, or the directional derivative of vector field y in the direction of x when we evaluate a P in M. Okay, so P in M. So first, when you start with these vector fields that are tangent to M, you can extend them locally, please, okay, to some neighborhood in R3, and you can talk about taking the directional derivative in the standard Euclidean. So as an analyst, right? So this is some vector field or vector if I evaluate it like this. It's a vector, points in some direction. You can think I can decompose it into a normal piece, not normal, tangential to the submanifold, and the normal one like this. So I could write it like that. E for tangential, and for normal. Okay, so this is as an analyst or linear algebra, but as a geometer, these pieces you can show, they have a very precise meaning. Okay, this one, this is the so-called second fundamental form. Okay, the beautiful thing about this is that it's independent of the extension of the vector fields x and y. Okay, and it points in the normal. Okay, what is this? You can say, oh, yeah, I can actually use this since this is tangential. Okay, I can just use this to define what the directional derivative is, right? If I want a definition, well, what's the directional derivative on my submanifold? I could use that because it's tangential, but you can do better than that. It's not just any directional derivative. What I'm writing here as a name that used for many different things, Gauss formula, right? Gauss has many formulas, so this is one of them, okay? And you can show that it's not that this is just tangential, that this is exactly the natural Riemannian connection on your submanifold. Okay, so this is a really nice proof. So as a motivation, we could think, can we extend this to the Laplacian, this approach? And this is actually what we did in the latest paper that finally got posted in the archive in December. we're calling it the shape operator formula, because the shape operator comes up in the computations. Okay, so using this, and also there's another formula for curvature, you can derive following. So if we start with the Buckner Laplacian on R3, and actually, okay, more exciting. It's not just R3. Using this, we can do a hypersurface, any hypersurface in higher dimensions, so 2 and 3. Physically, sure, we're interested in surfaces, but it actually works n bigger or equal to 3. So this is the regular Laplacian on R3, and I restrict it now to my hypersurface. We get a formula that is different because now it's for vector fields actually. So this one's directly for vector fields. This one we needed divergence precondition. This one is very general. We don't need the divergence precondition. So the tangential part, okay, so we're focusing on the part that comes, you can do the analogy with the Gauss's formula, the tangential component. You will get the Buckner Laplacian on your submanifold or hypersurface. Actually, what I like about it is that you see Ricci explicitly showing up. But this is nice, that Ricci is explicitly written like this. There's another term that this is the dimension of your hypersurface. You have a mean curvature. There's a Lie bracket or a Lie derivative, right? So here's a Lie derivative for form. Here we have a Lie derivative for vector fields. We look at the tangential piece. Then there's tangential and the last one. You might be thinking this is long. Again, I didn't write one. So this is now back. This one is, I will make some remarks in a second. And you will see. Okay. We can also say exactly what the normal piece is, but again, coming from fluids, we really are motivated by the tangential piece. So again, we like this because we can see Ricci. Yes?
Is there an extra U in that second last term?
The
With
second.
quadratic if you-
Yes, thank you. Thank you, So this is the Buckner Laplacian on the submanifold. This is Ricci on a submanifold. This is the restriction of the Lie derivative of the vector field, and is the normal into your submanifold. And H, as I said, this is n times the mean curvature. Here, the tilde doesn't mean the Euclidean connection. And again, you can see here that what you're going to get depends on how you differentiate the vector field in the normal direction. So it depends where you really are applying it in here. And then there's the last piece here, which you see in some situations you could set this up that this is 0. In fact, on sphere, this term would go away directly. And see, so okay, given how general this is, what we started doing is we started plugging in this index. Sorry?
What is it, upper index for last term?
Upper index. So this one would.
That looks like a P. Is that P?
So T means that project tangential. So here we're taking the covariant derivative, the Euclidean one, of U. In the direction there's the sub x, right? The one that we have here now is more complicated. First, you differentiate the normal in the direction of the normal. And you could choose your frame that this would be 0. But there are also natural choices when it's not. Is it clear? Yeah.
Yeah, so this is the essential what you did, like you compute the divergence of gradient of U in the ambient space.
Yes.
Okay, and then you just restrict and decomposing tangential and normal. So everything on the right hand side is going to be
Yes. I have the T. Yes. And again, we can say what the normal is, but I would have been focusing on the tangential. So maybe last minute, right? So you see, like using this formula, you can start looking at different examples. And this is what we've been doing with Patty. We're looking at different submanifolds. And one thing that in a way one should start, what's the simplest example that you can consider? Even if it's boring, but just to see that you can learn something. So one example that we've looked at is R2 embedded in R3. Pretty boring, but not completely boring, right? We know what the Laplacians are. And even there, you can choose an extension that will not give you just the Laplacian. You can choose an extension that you plug into this formula, will give you the Laplacian that we know, plus some linear term. Okay, and the extension is divergence free also. So this one again doesn't need the divergence free. So how do you guide this as finding the right operator? So what we're looking at still is a lot to do. Why I like to retire, so I can just keep working on this. There's a lot to do. So another direction to justify the operators is what sometimes it's called a thin limit. So you look at your surface or your manifold that you're interested in, and you look at a domain that's around it. So you go in some direction. So say we're interested in the sphere, you can thicken the sphere in both directions a little bit, and then solve the Navier-Stokes, right? We're interested in Navier-Stokes. Why are we just looking at the question? Let's look at the full equation. Okay, solve the Navier-Stokes in 3D, okay, and take a limit and see what you get. Somebody already did this. Okay, the Mam and Zayen have a paper from the 90s where they do this. And since you have a boundary now, you need to choose your boundary conditions. So they work with the curl of views of vorticity, and they look at the cross product with the normal. They assume that's 0, and they get the Hodge Laplacian in that setting. Then there's a sequence of papers of Murat where he's using the Navier boundary condition, and he can show that he obtains the deformation Laplacian or the Ebin and Marsden Laplacian using those conditions. So we're looking at that procedure now, and we modified it slightly, and it's still under construction, but it looks like if you make a change, you will not, that will also affect, even if you have the same boundary conditions, that can affect the choice of the operator that you get. If you're looking,
That's already started.
I think that's more general than the sphere. Okay, I think I'll stop. Thank you.
I'm wondering if there's like some physical arguments for why we should want this Laplacian to behave well with respect to.
See, I think.
Can you repeat the question for the?
So the question is, are there any physical arguments that one could make why the Laplacian should behave well with respect to the restriction? I think that's a good question, and I think the most physical I can think right now would be using this thin limit approach. That somehow you think about that it's an approximation, and how is the fluid behaving in the 3D domain, and see what would happen if you take the limit. That's the best way. I'm not saying that's the way, but you see, ideally, I would like some physical arguments, even if you don't like the hyperbolic space as much as I like it, right? Since we're looking at the ellipsoid, the Earth is not even a sphere, right? And actually, another thing, maybe you start looking at this, and I think why Tsuyoshi is interested is because of the Jupiter. Jupiter is much less of a sphere than Earth, and there's some physical phenomena that's not fully understood on the Jupiter. And if you use the model for using the sphere, and even if you use the deformation Laplacian, so you have 2 copies of Ricci, the model doesn't predict. Marcelo is making faces at. Do you have comments I would like to hear? I think it's hard, right? So I think the idea is different perspectives and see what we can do. So even in the case of having, you assume you have a sphere and you have the Ricci term, the model doesn't predict the phenomena that happens on the Jupiter. So the idea was maybe we can find the right Laplacian on the Jupiter that could work. I don't know. But this is, I don't know if it's gonna work, but it's very interesting. So I would like to see what happens. Yes?
I just have a couple of comments. I think that argument is really good of the limit because we think of water falling on a surface, right? It's not really two-dimensional. We approximate two-dimensional, but this problem is still two-dimensional, right? It's still like the water is on, so it's still like a two-dimensional problem. You can approximate by two-dimensional one, just water falling on a surface, right? But other than that, like, so I got involved in this paper to Magda mentioned because I've been thinking about this problem from the physics perspective about disposable activity. So that's how we started talking about it. So I spent a lot of time talking to physicists about this, right? And they don't agree on if this argument is right? So that's why you have a lot of different views of activity as well, right? So I don't think we're going to be able to settle with just one. Maybe there is one. I don't know.
So if your approach views the Euler equation and the velocity field form in the Navier-Stokes equation in that same form as the fundamental ones, and so vorticity transport would be the consequences of A. If you, and I care less about the physics, I just want beautiful equations. So if I decide vorticity transport is the fundamental thing, in 2D that you have the Laplacian of the vorticity showing up in that equation, but then when choosing one of these Laplacians might break some other aspect of that.
Right, you have Biot-Savart law, and actually, Jean Wayne mentioned this, Biot-Savart law. Could you, right, because vorticity is a function, right? So could you somehow have a Biot-Savart law that would allow you to recover velocity from that, which is another direction which we actually started looking at with, we're looking at Biot-Savart law with Jim Kelleher and Elaine policy from the Euler perspective. So finally, I'm learning about Euler. Yes, yes. No, that's a very good point. Yes. But again, it's another direction to pursue. So I don't know what will happen.
Just to have the exterior derivative community with whatever operator. Is that what you're sort of thinking? You were saying if I'd like to have a relationship between the vorticity and the velocity equation. The vorticity equation, you take the exterior derivative.
It certainly helps if you're the operator is with your Laplacian operator, right? And
yeah.
If you have, so in the original paper, you shouldn't even do this for manifold Einstein, which I would agree with. I don't believe Jupiter is a real thing because real time is perfect spheres. So in the Einstein case, of course, the D operator doesn't mean to any of the Laplacians, I guess. In the non-Einstein case, you're going to lose something, and I don't know what's going to be.
Okay, so in the Einstein case, you're saying D commutes to pretty much anything.
I think so.
I don't know.
Well, anything is a very strong statement,
Yeah, no,
but
The three reasonable choices.
Okay.
All those.
right, they would commute with Ricci, right? Yeah. Right. So the question just people was more about the vorticity, right? And I think again, they're very interesting questions and how do you think about all this. So maybe another thing that I could say is that at this point, what I think is I think the answer will depend on the problem that you would like to study. Okay, that I think at the end of the day, maybe everyone can be happy. Okay, and we can all just get along. That I think for my feeling is that on Einstein manifolds, for many physical phenomena, the Ebin and Marsden operator is the right one. But I think for some situations, maybe even Hodge could work, which I should, well, okay, Hodge work. There's no problems with Hodge on the sphere, I should say, with the hyperbolic argument that we have. Okay.
Yeah, so these are actually two different things. Like one is like just in terms of Laplacian, but then there's the Stokes equation.
Yes,
right?
yes.
Stokes equation. The fundamental thing that you want is like an energy estimate, right? So I look at the energy estimates for this complicated.
Well, this is just the beginning, right? Because you see, another thing, and right, no one. The way it's written right now, it's not. I should do a pullback to the surface. This is somehow you want to write it in terms of intrinsic quantities on your surface. Right now, it's not. So we're in the process of trying to clean this up. right? I think this is the first step, but I think the formula is nice. And again, especially if you start thinking about the Gauss's formula from that perspective.
But can you get global? And if your principal part, thinking uniformly elliptic, you can almost always get. You're always going to be able to get global existence, I guess, for any of these choices.
So
or is
see,
that-
there-
is that not-
This is too strong. We're not there.
It's functioning in the beginning, right? So for the order of Laplacian is gone, we don't get anything else.